Hello, and thanks for using TickBoom. In this video, I'm taking a look at the fifth of 6 questions in a set of questions that are focused on calculating volumes using rotation. So we're on the home stretch with these questions, and if you haven't already taken a look at my videos on question 1 to 4, I'd recommend you go take a look because you'll need to have understood those as background to this question. This question 5 follows on directly from question 4. So question 5 says to prove the result from the last question using the following process and ensure that you draw relevant conclusions and justify all connections. And so we're given this diagram, and then we're told the above diagram shows the area A bounded by the smooth curve y equals fx for x between negative a and a. So it's the area bounded by that and the x-axis. We're told fx is an even function, so that basically means fx will be equal to f of negative x. We're going to rotate this area about the line x equals negative s, where s will be greater than a, where a is just one of those constants that we're given. And that will generate the volume capital V, and we're going to use the method of cylindrical shells. So we'll have two typical strips of width delta t, whose center lines will be a distance t from the y-axis, and they're shown on the diagram. Alright, so this question 5 has 3 parts. Part A says to show that the indicated strips generate shells of approximate volume given by 2 pi f of negative t s minus t dt and 2 pi f of t s plus t dt respectively. Part B then says to show that the total volume of the solid will be V equals 2 pi SA, capital A. And then part C says to demonstrate that this proves the conclusion made in question 4. Alright, so for this question 5, as with all of these questions, a diagram is going to be helpful. So what I'll do is I'll just create our axis. So we'll have x and we'll have y, and we're given this curve that goes between a and negative a, so maybe I'll call this negative a, and this is the origin, and so this will be a, and we've got this curve that basically looks like this. It kind of comes up and then comes down, then comes up and then comes down. And the key thing to note, I haven't drawn it perfectly, but it's an even function, so it kind of should be a mirror image on either side of this y-axis. We're then told, maybe I'll use another color, we've got this value of s, or the line that's going into the negative axis a distance of s, so it's actually the line x equals negative s, and maybe I'll just put that here. So this line is x is equal to negative s. What else are we told? We're told, maybe I'll put in another color, we've got these 2 strips that will be that are at points t and negative t respectively. And that's pretty much the setup for this question. So for part A, we want to show that the volume of the cylinder generated from each of these strips will be 2 pi f of negative t s minus t dt, and then 2 pi f t s plus t dt. So kind of, we basically just need to use cylindrical shells on each of these to kind of generate those volumes. So what I'll do is I'll do it for f of minus t, and then we'll kind of hopefully be able to use the same approach to see what would happen for f of t. So if I look at f of minus t, and we're rotating about this line x equals s, so what's the distance here? It's 2.5, so kind of want to come the same distance. So basically, if I rotate this strip around, we'll get this cylinder, which is hopefully a process that's becoming more and more familiar as we work through all of these questions. So if we then unwrap that cylinder to get a rectangular prism, a thin rectangular prism, the volume of that prism, so the volume of, I'll just call the volume of, I'll say the cylinder from rotating the strip at negative t, what will that be? Well, that will be equal to, well, what's the circumference of this circle going to be? Well, it's going to be this radius, 2 pi times the radius. And what's this radius? Well, the value here is basically negative s. So we've gone a distance s less the distance t, both in the negative direction. But that distance there is basically s minus t. It's that difference. So it's going to be 2 times pi times s minus t, being that radius. So that's going to give us the circumference multiplied by the height. And the height here is just simply the function at negative t. And then we've got the width, which will just be dt. Because we're told the width of the strip has a width of dt. So if I just rearrange that a little, you get 2 pi f of negative t s minus t dt, and that's what the question asked us to show. So that's the volume of the cylinder generated from rotating this strip at negative t. Now what happens if we rotate the strip at t? So it's going to rotate a bit further. I won't draw it on, we probably don't need to, but it's basically the same process. So if we do the volume of the cylinder from rotating strip at positive t, what we'll get is, now we want to ask, it's going to be 2 pi times the radius of this cylinder. The radius will be now from here all the way to here. So this distance from here to here is s. That's the magnitude, plus t. So we're going the distance s plus t. So that's going to be s plus t. The height is the value of the function at t, which is f of t. And then the width of the strip is still dt. So again, just a minor rearrangement to put it in exactly the format that the question had it. And that's what the question wanted us to show.
Panic boom!
So that's part A done, kind of just getting our heads into the space of how the cylindrical shells are playing out for this particular curve. Now for part B, I'll just note here, part B, they want us to show that the volume from rotating this whole curve around the axis, that volume will be equal to 2 pi s, being this value s, and then capital A being the area under this curve between negative a and a. So that's what we want to show. Basically, the way we can get there is we can start by kind of taking these two strips or these two results that we've done in part A and kind of splitting up this curve into two bits, the bit between negative a and naught, and then the bit between naught and a, and adding up those integrals. So we can start by saying the volume will be equal to, first of all, this bit here being rotated, so the integral from negative a to naught of all of the strips in that range. And we've just worked out in part A that that's going to be 2 pi times f of negative t times s minus t dt. And then adding to that, we'll do the volume from this part of the curve, which would be the integral from 0 up to a of these strips here. So this will be 2 pi times f of t s plus t dt. So that's what we need to evaluate. I might need to just turn over for space. So continuing part B, we'll say our volume is equal to, and I think the first thing I can do is this f of negative t, I'm just going to write that as f of t, and I can do that because we're told that the fx function is even. So f of negative t will equal f of t. So the volume will equal the integral from negative a to 0 of 2 pi f of t, and then we've got our s minus t dt, plus the integral from 0 to a of 2 pi f of t s plus t dt. And what I might do is I'll bring out these 2 pi's, which are just a constant with respect to t. And then we'll have our, if I now just expand each of these, so the s minus t and the s plus t, we'll get the integral from negative a to 0 of s times f of t minus t times f of t dt, plus the integral from 0 to a of s times f of t plus t times f of t dt, and that's all within the brackets. Now, what I can do, this minus t f of t and plus t f of t, they're essentially going to cancel, and that's because the area under the integral between negative a and 0 and 0 and a, if we kind of think about what the curve is, that because it's an even function, those things are going to take the same value. The area under the curve, t times f of t, negative t f of t and plus t f of t, they're effectively going to cancel each other out. So what we can now do is we can now factor out this s, because again s is just a constant with respect to t. So we'll have 2 pi s, and now we'll have the integral from negative a to 0 of f of t dt plus the integral from 0 to a of f of t dt. Now actually it makes sense at this point to bring these together. So we get 2 pi s times the integral from negative a all the way up to a of f of t dt. And that we can write as 2 pi s times a, since we're told that a is the area under the curve, which essentially is another way of saying it's the integral from negative a to a of f of t dt. That's what the area under the curve is defined as in terms of calculus, the integral. So that's it. That's actually that's how we can show that result. So that's as required. That's what part B was asking us to show. So now that leads us to part C, and part C wanted us to kind of link up this result we've just shown with what we showed in the prior question. And so if we go back to question 4, or even actually question 4 linking to question 3 before it, this circle here is essentially the equivalent of our f of t, our kind of function here. In question 3 and 4, which are linked, this circle is essentially what we're dealing with. So that's A, that's our kind of A. What's the area inside this circle? We could call that A. And so what we could say is that thinking about this structure, A would be equal to the area under this circle. Well, if the radius is d, it would be pi times d squared, which is the area under the circle, or the area inside the circle, basically. So that's what our A would be in terms of question 3 and 4. Now, what would S be? Well, S is basically S is the distance. If we come back here, S is what we're rotating around. So it's the distance between what we're rotating around and the center of the curve. In this question 5, it's basically the center of this curve is 0, and so the distance there is S. Now, if we come back to our original curve, well, we're rotating around the y-axis, and the center of our circle, the distance between the y-axis and the center of the circle is E. So effectively what we can say is that S would be equal to E, which is the distance between the axis of rotation, I'll call it, and the center of the circle, or the center of the curve, which happens to be a circle in our case. So therefore, we can say that if we're going to apply this result, the volume of the curve in question 3 and then 4, which were linked, we could write as 2 times pi times E times A, which we've said is pi d squared. And so we can write that as 2, the pi's come together as pi squared E d squared. And if we go and take a look at question 4, 2 pi squared E d squared, and that was consistent with 3, which is 2 pi squared E d squared, which again we had checked anyway using our general formula. So again, we've got yet another way to verify that what we had worked out in question 3 and then checked in question 4, question 5 gives us yet another way to get to that result. So it's all giving us more and more levels of comfort that there haven't been any mistakes. And yeah, question 5 actually is quite interesting because we've generated this kind of quite generic result. So it's quite a good question to have worked through to kind of consider, well, how much should we apply this? Like, in what other circumstances could this be useful? And we see, well, at least with the generation of a torus, it's another fairly elegant way to get to that result. Boom! So yeah, hopefully you found that explanation helpful. If you did find it helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom!